Welcome to the AP Computer Science Principles Practice Questions Test Prep Series. So today we're going to take a look at big idea number 2, which is abstraction. I'm going to go through some questions hopefully to help you bring up your score on the AP test. So question number 1 says, which of the following are considered abstractions? So let's underline that word, pretty important. Are considered abstractions, so right here. In the use of cell phones? Well, first of all, when we're thinking about abstractions, when we think about what they do in day-to-day life, they basically hide detail. They make more complicated ideas simpler. So if somebody said, pass me the chair, they are actually abstracting in language. They're combining a bunch of ideas, like a chair has 4 legs, it has a seat, it has a back. So when someone says, pass me the chair, they don't need to say, pass me that thing with 4 legs and a back and a seat. They abstract, they collect a bunch of ideas into a single idea, which makes it a little simpler, and the detail is hidden. So it says, which of these are considered abstractions in the use of cell phones? So one says a mobile application written in a programming language. Okay, so let's think about this for a second. So we've got a mobile app and it's written in a programming language. So the language itself is the detail, all of the detail that goes into the single thing called the application. So therefore the application is the sum of all of those parts, including all of the code and language that makes that. So therefore, I would consider this an abstraction. Next, number 2, the phone's hundreds of millions of transistors act like switches to represent ones and zeros. Well, ones and zeros are the bits, the data that's being transmitted at the most basic level through the phone. So physically, this is a type of abstraction. Those physical transistors are acting like switches. So therefore that is an abstraction. And then number 3, the icons on the screen representing the applications. Well, let's think about opening an app without a little thumbnail, without an icon. How would you do it? Very difficult to even imagine that, right? Maybe you would just have pages and pages of code, and then you'd have to select part of the code, which would be impossible, and it wouldn't make apps as easy. So the actual icon is representing the app. The icon is the sum of all of the parts of the application and all of the code and all of that other stuff as well. So really, this is an abstraction. When you see that icon on the screen for opening up iTunes or your messaging app or whatever, that is considered the app itself, and so that is an abstraction. So our answer for number 1 is D, because 1, 2, and 3 are all correct. All right, number 2, let's take a look. All right, so numbers can be represented in multiple bases. For example, in the octal system, so oct, just like octopus, we think 8. So we can represent 8 digits. Numbers in octal can be expressed by writing the number followed by a subscript 8. So notice what I'm doing as I'm going through this question. I'm underlining and I'm circling, or I'm scribbling, writing little notes next to it. So all of this is helping me understand the question. Okay, so followed by a subscript 8 indicating that the number is an octal digit. Convert 24 subscript 8, so 24 sub 8. So now we know that 24 is in octal, and they want us to convert it to decimal. So let's take a look. They want us to convert this number to decimal. Well, 24 sub 8 is what we're given. So we know it's based in octal. So therefore we should begin, or one easy way to begin is by writing the base, which is the 8, to multiple superscripts almost. So this is 8 to the 0 power. This is 8 to the first, 8 to the second, 8 to the third. Now we could keep going, but we don't need to, because this 24, which is written in octal to base 8, only has 2 digits. So what we're going to do is we're going to slide those over here, and we're going to push them against this wall. So the 4 goes underneath the 8 to the 0, the 2 goes under the 8 to the 1, and what we end up doing is we multiply these out. So this is going to give us, right here, this is going to give us 2 times 8 to the 1, which is going to equal, well, 8 to the 1 is 8. 2 times that is 16. And then over here, this is 4, because there's a 4 there, times 8 to the 0. Well, 8 to the 0 is 1, so 4 times 1 is 4. And then what we do is we just add them. So 16 plus 4. So that gives us 20. And so 20 is our answer. So remember what we just did? We just converted 24, which was with base 8, into some number with base 10. And so that answer we just calculated is 20. Now keep in mind this is a decimal number. And in the past we learned about decimal, about binary numbers, about octal, about hexadecimal. We learned about all of those different types. This 20 we just converted into decimal. So that was number 2. Okay, question number 3. Let's take a look here. Okay, so question number 3 says, what base could the number 18 be written in? So this time we're given the number 18, but we don't know the base. We don't know the base. So we're asked, could it be written in octal, base 8? Well, let's think. If it was written in octal, then that would mean we'd have our 8 to the 0, 8 to the 1, ... And then the number itself, if we slid it under, would be a 1 and an 8. So let's think, is this possible? Are we allowed to have 18 written in octal? Well, there's a problem here. If you are, let me just change the color as well. If we are writing something with base 8, that means that every single digit must be less than the base. So that means less than, in this case, it must be less than 8. Now the reason for that is that this 8 times 8 to the 0, well, that's 8. So really this should not live in this slot. It should live over here as an additional 1 to this one. So that should really be a 2. So let me explain a little more. If we're thinking about the number 20, all right, and I'm going to put 10 here because really when I say 20, I'm talking about regular numbers, about decimal. Well, this is your tens place, and this is your ones place. So here we see that 20 is really 2 tens and 0 ones. But isn't 20 also 1 10 and 10 ones? That's true, right? 20 is really 1 10 and 10 ones. That's together they're going to give you 20, so it has the same value. But we can't put 10 in this one digit because a 10 in this ones place should really be a 0, and then we should move the 1. We should carry the 1 over here. So really we should write this as a 2 here and a 0 here to maintain that as 2 digits. So it's the same thing. I'm just going to change over to blue. It's the same thing. If you're writing 18 and you're saying that this is an octal, then really this second digit has already maxed out. And once it gets to 7, it's got to be very careful, because if it moves to 8, then this really should say a 2, that 8 becomes a 0, and then carries 1 over to the next place. And this really should be this. So keep in mind, the easiest way to remember this is that there is a problem if the digit itself is the size of the base or greater. Just like we can't have a 10 in the ones place, we also can't have an 11 in the ones place, can't have a 12, but we can have a 9 in the ones place. So anything less than the base, anything less than this base is allowed to go in one position. Okay, so therefore, what base could the number 18 be written in? Well, it cannot be written in octal. So therefore, anything that says 1, here, here, and here is not the correct answer. So therefore, our answer here is C. So our answer for number 3 is C, just by elimination after we realize that 18 cannot be written in octal. Okay, next question. Okay, so this is question number 4. So it says one way of, that should say of, not or, one way of representing colors in HTML is in hexadecimal, such as FF, EB, 5A. or as an RGB value such as 255, 235, and 90. Now, these express the red, green, and blue values in decimal. So I'm going to just highlight a couple of things. This is the red. This is the green. And this is the blue. Now, that doesn't mean that there's only one number for blue and one number for green and one number for red. It just means that because there's different shades. There's different shades of blue, different shades of green, and different shades of red. So 90 represents a particular specific color of blue, and the same for the green and the same for the red. Okay, now it says the first two digits in the hexadecimal, so keep in mind hexadecimal is talking about this thing over here. It says the first two digits of the code correspond to the decimal representation of the red value, and then the green, and then the blue. So let's do the same again. So the red is represented by these first two digits, first two characters, and then the green over here, the next two, the E and the B, and then the blue is the next two. And it says, right now we're at this part of the question, which of the following hexadecimal values correspond to the RGB value of 0, 255, and 213? Now, as I did this in class, students tried to connect the 255 equals the FF, and the EB equals the 235, and the 90 equals the 5A. But as I read this again, we can't definitely connect that this hexadecimal is the same as these decimal RGBs. We don't know that for sure because of the wording here. So when the question asks us, which of the following hexadecimal values correspond to the RGB value 0, 255, 213, we have to do some conversion. So all of these numbers here are written in hex, which we know is base 16. So we are trying to figure out the first two digits if they, so I'm going to box up each of the first two digits, if they correspond to this decimal value in the RGB 0. So let's take a look. 0, 0, which is in hex, so let's write a little 16. Does it equal question mark? Does it equal 0 in base 10? If this is true, then we know that the start of our hex has to be 0, 0. So I'm going to change the color just to remind us how we're doing this. 0, 0 written in base 16. Well, if we're dealing with base 16, we write 16 to the 0, 16 to the 1. Now we could keep writing, but what we've got here are only two digits. So those two digits slide down, 0 and 0. So when we do the math, 0 times 16 to the 0, well, 16 to the 0 is 1, times 0 is 0. And so 0 times 16 to the 1, well, 16 to the 1 is 16, times 0 is 0. So when we do 0 plus 0, we do get 0. So therefore, this is correct that 0, 0 in hex is the same as 0 in decimal. So straight away, we know it's either A or it's C, because those are the only two with 0, 0 at the start. So we can cancel B and D. So now we need to check another fact. Well, we could try and look at the middle. However, these are both probably going to be correct, and they both have FF. So even if we know it's FF, we can't cancel either A or C, which we need to do. So the next thing that we need to look at is comparing these two, D5 versus E5, to figure out which one gives us the 213. Which one of these is going to give us 213? So when we take a look at this, we're going to think to ourselves, well, here we don't have a 0, 0. We've got, let's just look at D5 to begin with. So D5, I'll change this color. D5 is written in hexadecimal, which is base 16. So again, let's put our 16 to the 0, 16 to the 1. So there's two digits here, two characters. The 5 goes under here, and then the D goes here. Now, That's a little strange how there's a letter, but that's how hexadecimal works. We start off with 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we don't put a 10. We then go to A, B, C, D, E. So keep in mind that this is 10, 11, 12, 13, 14, and also we have the F, which is 15. Now if you count them, you might think that, well, this is just 15. This isn't hex because it should be 16. But in fact, it is 16 because of this 0. So it always helps me to quickly write this chart out, because now we can see that this D has the value of 13. So D has the value of 13, whereas 0 has a value of 0, 2 has a value of 2, but then it gets a little different when we get up to A, because A has the value 10 and so on. So over here, this D we could replace with 13. So when we do the math now, just going to bring this over here, we've got 16 to the 1, 16 to the 0, we've got a 5 under here, we've got now a 13 because that was D under here. So okay, so we're multiplying these out. 16 to the 0 is 1, and 5 times 16 to the 0, well, that's going to be 5, because that's 5 times 1, which is 5. And then over here we've got 16 to the 1 is 16 times by 13, so 13 times 16. So let's quickly do this. 10 times 16 is 160. 3 times 16 is 48. So when we add those up, we get an 8, we get a 0, we get plus the 1 is 208. So now when we add the 208 and this 5, we do get 213, which matches this number here. So straight away we know that our answer is A, because the D5 is the appropriate hexadecimal for the 213 number, which is written in decimal, whereas the E5 would give us a different number, not 213. Okay, so question number 5. Before we start it, consider these two numbers, 20 degrees Celsius versus 25 degrees Fahrenheit. Which one is hotter? Well, if you jump for the 25 thinking it's warmer because it's a bigger number, you'd be wrong. So the units that were given, Celsius versus Fahrenheit, are very important, just like the base that were given with these numbers, the 10 and the 2 and the 16, which represents, so base 10 is decimal, base 2 is binary, and base 16 is hexadecimal. So these are very important. So the only way to compare 20 degrees Celsius and 25 degrees Fahrenheit is to convert them all to the same unit. You could convert them all to Fahrenheit, you could convert them all to Celsius, but when they are the same unit, then you can say which is the bigger or the smaller. So the numbers we use the most often in day-to-day life is decimal. So let's keep with decimal. So we've got 100, which is this one. Now let's try and convert this one to decimal. So the 1011010, which is written in binary. So this is my way of doing it. I put a 2 to the 0, 2 to the 1, 2 to the 2, and I keep doing this until I get to the end. 2 to the 4, 2 to the 5, 2 to the 6. And to convert this to decimal now, I go through each of these numbers multiplying. So 0 times 2 to the 0, well, 2 to the 0 is 1, times 0, 0 times 1 is 0. So this is worth 0. And in fact, all of these, when you do 0 times anything, you're going to get 0. So I'm just going to actually cancel these out. I'm going to focus on the others. So 1 times 2 to the 6, well, 2 to the 6 is 2 times 2 times 2 times 2 times 2 times 2. So quick way of doing this, 2 times 2 times 2 is 8. And the same again, 8. So when you multiply these, you get 64. So this first number here equals 64. And then over here we got 1 times 2 to the 4th. So 2 to the fourth is 2 times 2 times 2 times 2, which is going to give us 16. Then over here we've got 1 times 2 to the third, so that gives us 8. And then we've got 1 times 2 to the first, which equals 2. So now what we've got to do is add up all of these. So 8 and 2 is 10, so then plus 16 is 26. So we have 64 plus 26, which when we add them up gives us 90. So this number here equals 90. So straight away when we're asked to put the following in order from least to greatest, we know the binary has to come before, which is 90 in decimal, has to come before the decimal, which is 100. Now we don't know where the other one fits in, but we know the binary is before the decimal. So as we look through this, in A we've got the decimal before the binary, so we know it's not that. And then where else? So we know the binary has to come before the decimal. Well, here the binary is before the decimal. Here the binary is after the decimal, so we know it can't be C. And then here the binary is before the decimal. So it's either B or D right now. So now we need to convert the hexadecimal, so 6A to the 16. So keep in mind, just like the chart we did before, where we went 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 10 was, let me do the chart again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 would be A, so that equals 10. And then B would equal 11, C would equal 12, D would equal 13, E would equal 14, and F would equal 15. And so those are 16 items there because of the 0. That makes it 16. And so in this case, we're dealing with hexadecimal, so that's base 16. And we could keep writing this, but we only have the 2 digits. And so the A, which is equivalent to 10, goes right here. And then the 6 comes right under here. So when we multiply this out, we've got 16 to the 0, which is 1. So 10 times 1 is 10. And then we have to add it to 6 times 16. Well, 6, because 16 to the 1 is 16. 6 times 10 is 60. 6 times 6 is 36. So when you add them, 60 and 36, you get 96. So 6A in hexadecimal is worth 106. So therefore we know that the hex comes after this, because the hex in decimal is worth 106. So as I look through this, we need the hex at the very end, which out of B and D is going to be D. So we know that D is our answer. Okay, next question, let's take a look. Question number 6. This question says, which of the following is not a common number system utilized in the representation of data? Well, base 2 is binary, and that's when we deal with zeros and ones to represent bits. So that definitely is used in the representation of data. Base 10 is decimal. So those are just like regular numbers we use every day, counting numbers, integers. And so those are used, yeah, very common. Base 16 is hexadecimal. And hexadecimal is used in the color codes, just like we saw before, FF, 0, 0 to D. And even the decimal is used in colors when we do the RGB. And each of those numbers are written as regular decimal numbers. So we get to the bottom, base 32, and so this is a little more unusual. So which of the following is not a common? So if it's not common, it's unusual, and so D would be our answer. Number 6 is D. Okay, number 7. Okay, so there's a lot going on here in number 7. So it says, which of the following procedures will correctly remove all multiples of num from num list? So this is often where students start pulling their hair out because it gets a little trickier. But let me try and break it down so it's a little easier. So we need to remove multiples of some number from some list. So let's just think about what multiples are. If we look at the number 5 and we look for multiples, we've got to be careful we don't confuse this with factors, because these are in fact multiples. So if we had a list such as 1, 2, 10, I don't know, 15, and we need to remove all multiples of this number from this list, we would want to remove the 10 and we'd want to remove the 15. So let's in fact use these numbers here as an example to help us get through this problem. So let's say that, if I just change this color, let's say that the 5 is the num, and let's say that this thing is the num list. So let's see if the first one does it. So we're looking just through here to evaluate whether I works or not. So the procedure is called remove multiples. That's just a name they're giving to it. And then inside there we've got 5 and then 1, 2, 10 and 15. We're just using the numbers that we made up to help us get through this problem. So it says for each item in this list, if num mod item, so the num we've got is 5, the item would be one of these numbers. Okay, the item would be each of these numbers as it spirals through, as it cycles through. So if, let's take the first one. So if 5 mod 1 equals 0, then we're going to remove from the num list the item. So let's think how mod works. Mod is the remainder after the division. So 5 divided by 1 equals 5, and the remainder is 0. So in this case, 0 does equal 0. So what's it going to do? It is, because it says if this is true, well, if 0 equals 0 is true, which it is, then it's going to remove it. But should it be removing 1? That's the big question. Should we be removing this first item from the list? Because the question says which of the following procedures will correctly remove all multiples of the number from the list. Well, 1 isn't a multiple of 5. It might be a factor, but it's not a multiple. And so this wouldn't do the correct thing, because it would remove 1 when really up here we see we only want it to remove the 10 and the 15. And so I is not one of the correct answers. And so even in our answers over here, A, is 1 only true, or is 1? We know it's not A, we know it's not C because of these things. Okay, and just a reminder, a repeat of this. This is a little more difficult to do unless you use these number examples for num and num list. But by understanding what the question's asking you in this cloud up here, and then by using these example numbers, makes it a lot easier to get into this question. So let's check the next one. The procedure is remove multiples, and then again we use our example 5 from 1 to 5, 10, and it says give n the value of 1. Okay, so n has the value of 1, and then it's going to repeat length num list times. So in our example, our num list has 4 items, so this is going to repeat 4 times. The first thing inside the repeat is that it's going to give n the value of 1. So that seems pretty important here, because it's going to do this every time it repeats. It's going to give n the value of 1. So num list, and then bracket, and then 1. Let's think about what this means. Num list, bracket 1. This means the value of item 1 in num list, which in this case is 1. And it says if 1 mod number, well, num is the 5, right? Num is the 5 because that's the number for the multiple that we're looking for. If 1 mod 5 equals 0, then remove it. And then, so let's think, is this true? 1 divided by 5, well, that equals 0.2. So the remainder is not 0. the remainder is not 0, so this is not true, so it's not removing it, which actually is good because we don't want it to remove number 1. So let's think what happens next. So now it gives n the value of n plus 2. Well, n was 1, and now it's given 1 plus 1. It's given that value. So now n becomes 2. So now it gets back up to the top of the repeat. Now if it kept n is 2, then it would look at the second value. And then when n went to 3, it would look at the third value, the third item's value. And then n is 4, it would look at... So that's kind of nice how it would keep doing that. But there's a problem here is that when it gets to the bottom of this repeat and has to go up to the top, n is given the value of 1 again. And so if n is given the value of 1 again, it ignores this. It's almost as though it shouldn't even be there. If it's going to ignore it, what's the point? So when n is given the value of 1, again, numList1 is going to be the value of the first item. So it constantly checks for 4 times, which is the length of the list, but each time it cycles through, it's always checking the first item. It never gets to evaluate the second, third, or fourth items. So therefore, procedure 2 is not working correctly. So if it can't be 2, we know it has to be 3 only. So we could go through this, but in the sake of time and test-taking strategies, we've cancelled out everything apart from 3, so it has to be 3 only. So that was question number 7. Okay, here's 8. Let's take a look what it says. It says a programmer has a choice between a higher level and a lower level programming language to use. Which should she use and why? Okay, so it's kind of saying that it's some kind of a choice here, right? Choice, and there's 2 levels of language. Okay, there's the lower and then there's a higher. Okay, so when we first think of these words lower level, we think that this is what we think. We think it's easier, right? We think that's what we're thinking, but it's actually not the case. When something is a lower level language, it means that it's broken down into more bits and pieces, like granular. It's broken down into lots and lots, many more, because each piece is smaller. Now, for a computer, that might be easier to handle, but for us, it's not easier because we've got more bits and pieces. So this is, in fact, harder for us. Whereas the higher level is... the higher level is actually easier because it handles itself all of the more difficult pieces. So all of those granular bits and pieces, ones and zeros, all of the code at its most basic level is grouped, and we're not handling it at that level. We're handling it from a higher level, which is making it easier for us to deal with. So, it's almost like shortcuts. If you have a key that you can press, that you can program to open up a document, and you just press this one key and it always opens up this document, then that would be seen as a higher level, because it's one key that you press and then it does all of the lower level stuff automatically. So with that in mind, let's keep going through this question. It says, what should she choose? So here it's saying that she should choose the higher level. Well, that's not saying that she should always choose the one that's easier. Well, there is a level of choice here. She doesn't always have to choose easier. Maybe different languages, different levels for different purposes. So therefore, this one just really isn't making sense for me, because it also goes on to say because the language itself will be less complex and there will be fewer errors. Well, higher level is actually easier. There's less complexity in there. Okay, B, the lower level, because there's more flexibility for complex programs. Well, maybe she's not making a complex program, but again, lower level is harder for us. So this one's not making much sense. Okay, C, it depends. Well, I like this because it does depend on her needs, as a higher level language will be less complex. Yeah, so easier, it's less complex, but it will not allow as much freedom as a lower level language. Okay, which is true, because when you have more and more details, more and more bits and pieces, there is a freedom of what to do with those bits and pieces. Whereas when it's higher level, some of those choices have already been made. So C is looking pretty good. Okay, now D, it says either language, because both languages will be converted to a lower level language and be executed on the computer. Well, this one isn't really highlighting the choice that she has and the particular reasons, but it is saying that either language, because both languages will be converted to a lower level language executed on a computer. Well, maybe this isn't true, and maybe, we don't really know the purpose of what she's using it for, if it's code on a website, if it's code on an application on a computer or on a cell phone. We don't really know exactly how it's going to be used, but saying either means that it doesn't really matter. But sometimes it does matter, and it does depend the purpose. So therefore, now I'm convinced the answer is C. Okay, because D suggests that they are equally weighted. Either language is okay, but that's not always the case. All right, so that was question number 8. Let's take a look at 9. All right, so 9 is looking at these procedures. It says consider the program code, display highway. So notice how we've looked at these before, even in these practice questions, but notice how there's a capital letter with the second word and they're pushed together. This is called camel case, because it kind of makes a hump, camel case. And so this is representing this program. And it says it displays several cars on a highway, and the program includes the following procedures: display the antennas, display the wheels, display the windows, display the cars, display the roads. So that's a lot that's going on. And it says which one of the following is an appropriate visualization of the program's abstraction hierarchy. So let's think about this. So there's a program, and it displays the cars on a highway, right? That's what it says. Displays several cars on a highway. So if I said to you, how would you draw this? How would you paint this? You might think, well, first of all, I need like the highway, right? I need the road. Right? I need the road. Okay, so that's the first thing. I need the road. Next thing that I need is I need a car. All right, so I need a car. So next thing is to put the car there. All right, and then what's the next thing? Well, then the next thing is that on this car, I need the window wipers. Okay, great. I need the wheels. Right, and the wheels have the spokes and everything. And then next thing that I need is I got more windows. Okay, got more windows on here. So as you see, the order that we go through this is from like the top level down. That's what it's talking about, hierarchy. An abstraction is, number 1, removing detail. Make things simpler. So when we think of a car, we think of the car, and then the abstraction is hiding all of the detail of all of these windows and whatever else is going on. So therefore, the closest match here is going to be, when you look at all of this stuff, is going to be D, because D is pretty much what I've drawn over here. It's the road first, then the car, and then the individual items on the car. So D is going to be our answer. Okay, number 10. This is the last question in the abstraction section, big idea number 2. So let's take a look. It says, consider the goal of flipping 2 fair coins simultaneously. So here you are, and you have just thrown 2 coins. Okay, you've just thrown these 2 coins. But you're going to do this 3 times. Okay, and consider 3 times and displaying the number of times number of times both coins land on heads. Okay, so the first time you could get head, or you could get head tail, tail head, or tail tail, right? So this is the first time, and then you got the second time, and then the third time, and the same things can happen: head tail, tail head, Okay, so as you see, I'm just writing out, this is what you call a sample space, which you learn in middle school and high school, probability math. So as you see, they want to know if you do this 3 times, how many times you're going to end up with this situation. Heads, heads, and heads. All right, which of the following code segments can be used to accomplish this goal? So let's go through each of them. Okay, the first one is A. So it says give A, set A to 0. Okay, which is a good idea because no coins have been thrown. And it says repeat 3 times, okay, because you're going to repeat this trial 3 times. And then it says if random 0 and 1 equals random 0 and 1, then add 1 to the count. And then do it again and then again to make sure that you repeat this 3 times, and then display, show that count. Well, let's think. For a head or a tail, they each have a probability of 1/2. Okay, we know that. So if we're looking at random, picking a number random from 0 to 1, we know that there is a 1/2 chance of picking 0 and a 1/2 chance of picking 1. So that seems pretty reasonable to look for random 0, 1. And also, at first, it seems reasonable to let that equal random 0, 1. But here's the problem. If heads is represented by a 0, and tails is represented by a 1, it doesn't matter if you switch these up, but let me just set them for heads is the 0. Then let's say that here it picks a head, and then here it picks a head, then this would add 1 to the count, which is what we want to do. But let's imagine, we just change this color, let's imagine that instead of it picking a head, it picks a tails and a tails. Does a tails equal a tails? Yeah, well then that would also add. And that's the problem with this code, is that we only want it to add when 2 heads are chosen and not when 2 tails are chosen. So there's a big problem with A, is that it's going to double count. It's going to count 2 tails over here as also adding to the count, which we do not want. So A is out of the question. Okay, B, change over this color. Okay, so B says set the count to 0, which I like, repeat 3 times, okay. Now it says if random 1, 2 equals random 1, 2, then add 1 to the count and display count. Well, this is almost identical to the one above. The only difference is that they have a 1 and a 2 instead of a 0 and a 1, but it's the same problem. If you get a head and a head, it's going to add 1. If you get a tail and a tail, it's going to add 1, which we do not want. So B does not work as well. And so next, over here it says repeat 3 times, which seems pretty good. Okay, repeat 3 times. It says set the count to 0, okay? And it says if random 0, 1 equals random 0, 1. So I'm trying to figure out what's the difference between these two. So when you look at A and C, there is a difference. Here, it's setting the count to 0 at the very start of each of the repeats. So it doesn't even matter if we do get a head and a head, and then it adds 1 to the count. Because what happens is when it comes to repeat this whole thing, the count is reset to 0. And also we have this problem of tails, and tails also adds 1 to the count at this point, but doesn't really matter because the count gets reset to 0 every time this runs. So therefore C doesn't look good, so it has to be D. Now we could look at this really quick, because we've got a 0 and a 1. Let's say that, this is a head. Well, let's say this is a tail and this is a head, and so 1 is a head, and then let's say 2 is like the other tail, because we've got 2 different coins that are being thrown. So this is still looking at a 1 in 4 chance of this 1 being chosen at the same time that this 1 is being chosen. There's still a 1/2 chance to choose the 1. There's still a 1/2 chance over here to choose the 1. So for both of these things to happen when you multiply, it does give you a 1/4 chance that random 0, 1 equals random 1, 2. And that's perfect because when you look at the sample set for the sample space for throwing one coin, or actually for throwing 2 coins in one trial, the probability of getting a half and a half is, when you multiply them, is the 1/4. And so this this simulation over here actually is working out, because this is a 1/4 chance and then add 1 to the count, and that count isn't being set to 0 because this block right here is not inside the repeat. It's only set to 0 right at the start, and then it repeats the stuff inside 3 times, which includes increasing the count if these two things are the same, and then display count at the end. So D is our answer. So this is the end of Big Ideas 2 abstraction section. I'm going to upload the other Big Idea sections as well. If this is useful, subscribe, and keep checking back in for more videos on computer science. Thanks.